You talking about this class?
Yeah, not because of you. It's just I wasn't having a good day. Now look at these notes. How big? I was like.
I get it. I get it.
No, because like you can tell on days that you can tell days that I'm like
Those are conscious days. And
ready to go, and then
those are conscious days. And
yeah,
those
like
are...
look at these drawings compared to like these.
Oh, I get it. Is this gonna?
You're gonna open AutoCAD again.
It just depends on the day. Look, this one's got fire.
There we go. I don't know if I'm in need for a new computer or whatnot these days. It's just a little slower and slower. So.
Yeah,
This is a newish machine too, so it's not that old. But what? Oh, are you looking at? Are you in the market for one?
So this one it keeps crashing, and I took it to IT. And yesterday at IT, it stopped turning on, so I was like, oh, it's done. So I ordered a new one, but right now it's on. Oh, I'm not running anything, and my CPU's at 50%.
Yeah.
So that's not good.
So it's a Surface. I think it's a Pro 9. It's not that old, but I don't know. All right. Something else. All right. So okay. I know.
No, his nose is the maximum.
Okay, that actually is pretty good. I'm going to give you that. All right, everybody, let's get started. I'm just going to lean into it and say, I'm sorry, I really wanted to get your homework or your exam graded by today. It just didn't happen. I think I'm about halfway done with it. All in all, it's going as expected, which is good. You know, I think everything will be fine. But I do need to get them off my desk because I'm going to have two big submissions. One is your project coming up soon, and the other is I have an exam in statics coming up in the not too distant future, so I really want to get them off my desk. All right, so other than that, everything's good to go. How did the Excel-based homework go? Did that go well? I'm hoping that went smoothly. And hopefully it was easier than the last one. That was the intent. Okay. So we only have, we've been doing shear and moment diagrams for a little while, so I want to just sort of give you a glimpse into the future in terms of what's left. We really only have three main topics left with shear and moment diagrams. Today, we're going to look at concentrated moments, okay? And we're going to look at it in two contexts. How do you deal with a beam that just has a concentrated moment on it, but then also how do you deal with a fixed support? Okay, because both of those have concentrated moments. Just the fixed support, it's a reaction. Okay. On Monday, we're going to deal with internal hinges. Okay, because we haven't done that a shear moment diagram with an internal hinge yet, and so that's going to be our topic on Monday. And we're also going to pepper in a topic on Monday which we haven't discussed, which is internal indeterminacy for beams and frames, which is pretty easy. It's just another I formula, just another plug and chug there. And then Wednesday, shear and moment diagrams for frames, which really the only thing about a shear and moment diagram for a frame is we take a shear and moment diagram for a beam and just do that to it. That's really all there is to it. I have another sort of on the side topic that I'm throwing in there at the end because the frame assignment is going to be really quick, and so I want to talk about aids for structural analysis, like structural analysis tools like aids. And there is so basically what that is a symbolic means of constructing shear and moment diagrams. And the reason I mention it is because it's what a lot of structural engineers actually use when they do a lot of routine structural analysis. And so I want to make sure that you see what they are and how they work. And then after that, we get into beam and frame deflection. That's going to be after this. So, sound good? All right. So we got a little while before our next exam, if that tells you anything. So, okay. I had some coffee go down the pipe and just can't get over it. All right. So what we're going to do now is discuss shear and moment diagrams with beams that are subjected to concentrated moments. The same relationships still apply. Like in my shear and moment lectures, I sort of throw these two slides like in front of every lecture, just to sort of make the point that we are still using the same relationship, the same approach. Shear and moment diagrams subjected to concentrated moments, we handle them the same way. Nothing really changes except for how we consider the concentrated moment, bless you, when constructing the shear and moment diagram. The concentrated moment is just that, a moment, okay? So when you construct a shear diagram, you ignore it. It's not a shear, it's a moment. But what that's gonna do is it's gonna affect the construction of the shear diagram, or the construction of the moment diagram when we get to the integration side. Because we've been summing up the areas and they've all been adding up to 0. This is where it changes a little bit. That's where this is going to be different. And then for cantilevered beams, it's really not gonna equal 0. And the best way of illustrating this is to really just go through it. So what I want to do is I want to construct shear and moment diagrams for this example and this example. We've already done these examples in terms of computing the support reactions. We did this one, we did this one a while back. Y'all remember this when we computed the reactions for this? And remember we said, okay, you've got the distributed load going this way, the 10 kips times 45 going this way, the reaction going this way. And then when we computed reactions, we just added 20. It wasn't 20 times 35, it was just 20 because it already is a moment. Y'all remember that? So, and we got this reaction and this reaction. Now let's actually use them to construct shear and moment diagrams. So let me open up the handy dandy notebook. Oop, that's statics. No IJK if you can avoid it, right? Okay. So here's the beam. And so what we're going to do is construct shear and moment diagrams for this beam. And again, I think my overall big point that I want to get across to everybody is that this problem is no different just because there's a concentrated moment present. It's just some of our intermediate calcs may require a second eye, I guess would be the best way of putting it. Okay, so I'm going to construct the shear and moment diagram for this. I'm going to do it the same way that I've been doing all of the other problems up to this point. So I'm going to draw myself some guidelines. Just to sort of, keep everything kind of neat and tidy. Let's strike our horizontal line for our shear diagram. And so we'll put that I don't know, about like that. Okay. And again, we're going to construct this the same way that we've constructed diagrams up till now. Okay. So, if I start at 0, what's the first thing I need to do? Go up 15.2. Okay. All right, so let's throw some letters on this. Let's see. We'll call this point C. We'll call this point D. We'll call this point E, just so that we can have a frame of discussion here. So let's go from point A to point C. So what happens from point A to point C? Somebody tell me.
-3 slope for 10.
Okay, so you're saying going down. What were you saying?
-3 slope for 10.
-3 slope for 10 feet, so it's going to be a linear path like this. And so if I'm at 15.2 and I go down, how much am I going down total? 30. So if I'm at 15.2 and I go down 30, that puts me at?
-14.8.
-14.8. So that's going to look something about like that, right? Probably about like that. And then we'll call this -14.8. Okay. So help me out. So that's this path. What about from C to B? What happens from C to B? Nothing, okay? So when you say nothing, what does that mean?
Stays flat.
Horizontal flat line. So that's going to go like this. Just like that. Okay. So now at point B, what happens? Goes up to what? Positive 10. So that's going to look something, I don't know, about like this. Okay. So from B to D, okay. Now what happens at point D? And what would how would that affect the shear diagram? It wouldn't affect it at all. This is a moment, it's not a shear. So what do I do with that 20-foot kip moment when I'm drawing the shear diagram? I ignore it. And I just keep on trucking. To right here, and then I have a 10 kip load bringing me back to 0. And that is our shear diagram. So the big thing to keep in mind is that because it's a moment, it doesn't do anything. It just, it is what it is. Okay, let's start doing some integration. And I'm gonna split this up into separate regions. I don't really need to do it for the purposes of integrating the shear diagram, but as we're going to see here in a bit, it'd be kind of nice to split these up when constructing the moment diagram. So what's the area of this? 10 by
20, 200.
well, 200 or 100 and 100, right?
Yeah.
Okay. What about this rectangle right here? This is 14.8 by 15. This rectangle right here. 222. Do I have a second? So, okay. All right. Now here we've got this triangular region here. So if we want to integrate this and integrate this, we got to figure out these distances, right? So what we'll do is we'll say, okay, we've done this before, so we'll call this x1, x2. I can do better than that. Okay. So x1 and x2. And let's take x1. We'll do that over here. How are we going to compute x1? Like, how are we going to get this distance? There's a simple way of doing it. We take 15.2, and what do we do with it? Divided by what? The slope. And what is the slope of this line? 3, exactly. So, because that's the magnitude of the load over it. So, that's going to be 5 and some change, right? Yeah, so like 5.067. And then x2 is, and we can just leave everything positive because we're just doing distances, because it doesn't really matter. And that's going to be like just shy of 5, like 4 and, there we go, 4.933. Do these independent values make sense? I mean, what happens when you add them up? You get 10 foot, and that's what that total distance is. That part makes sense. Okay? So, therefore, what would this area, we'll call it area 1B. Let's call this area 2. What would these areas be? 38.51. Do I have a second? Second. Okay, so we'll call that 38.51. Okay, what about the second one?
36.50.
36. Is it 50 or 51?
I think it's 50. It's 504.
Okay, this might be rounding and whatnot. We'll leave it as 50, but it's so you'll see what I mean. You'll see what I mean. Tell you what, let's do this. Let's just call it 38.5 and 36.5. Let's just do that. I'm doing that basically because I don't want what's coming next to be a confusion just because of trailing decimals. Okay, that'll be close enough. All right, so far so good? So up until now, what happens if I add these areas up? What do I get? 0. Okay, let's see what happens. So I'll say note. So we have positive 38.5 minus 36.5. So maybe I'll throw a negative there just to make sure that's clear. We have a minus 222 plus 100 plus 100. Okay. What do I get when I sum these up?
Negative 20.
I get negative 20. Interesting. It's not 0, is it? So let's think about let's dig into this a little bit. Okay. Explain to me, when we draw a shear diagram and we add up these areas and the areas come up to 0, why, up until now, why did that have to be the case? Why did the areas have to add up to be 0?
Because the sum of moments is 0.
That's exactly right. The areas are the integral of the shear diagram, and the integral of the shear diagram is the moments, right? The sum of the moments must be 0, okay? Now, what we're finding is that the sum of the areas is minus 20, okay? So what we're finding is that the sum of the moments is not 0, but we're finding that for a very specific reason. And we're finding that because we ignored something. What did we ignore? The 20-foot kip moments. So what I'm saying is that the sum of the moments is 0 when you take that into account. So when we construct the moment diagram, I guess this would be a question. When we construct the moment diagram, are we going to consider that 20-foot kip a positive moment or a negative moment?
Positive.
It's got to be positive, right? Because the sum of the areas without that moment is negative 20. I got to have a positive 20 to bring everything to 0, right? If I consider that negative, this would be negative 40, and it'd make the problem even worse, right? So that's what that 20-foot kip moment is doing, is it's bringing us back into equilibrium. The sum of the areas is negative, so that has to be positive. Does that make sense? Okay. If that's the case, if that makes sense, then let's go ahead and construct our moment diagram. Okay, and we'll do about like that. I can do better now. I don't know if that was better, but that's close enough. Okay, so this is going to be our moment diagram. And one thing I'm going to do is I'm going to add another guideline sort of right there, because this is where the shear is 0, right? So if this is where the shear is 0, then I'm probably going to have some sort of peak value right there. So let's see if we can construct this thing out. So we'll call this, I don't know, point F, whatever, you know, because we have A, B, C, D, E. Let's call this point F. What happens from A to F? What happens from A to here?
Go up 38.5.
Okay, so I'm at 0, go up 38.5. I'm at 0. $38.5. Do I go up linearly or quadratically? Quadratically, okay. Do I do option 1, option 2? 1. In fact, what's going to happen is this is the same parabola. What is this point right here going to be? 2. Because I'm at 38.5 and then I drop down 36.5 and it's the same function, it's the same lines, it's just the same parabola going down to 2. Make sense? So if I'm at 2 and I drop down 222, what am I going to be right here? Negative 220. And what does that path look like?
Straight line. Linear.
Okay. So far, so good? Now let's just conceptualize what happens. Let's just look at our shear diagram and ignore what's going on above. Okay, so I'm at negative 220. So if I go up 100 and 100, I'm going up 200, that's going to put me at negative 20, right? That's not enough, right? So what's going to happen is this. I'm going to go up to minus 120. And then what's going to happen right here? A sudden jump upwards. And that concentrated moment right there is just like a point load. It's a sudden jump. Okay? Okay. Let me take a step back. Let's see, how are we doing? Does this make sense? Does anybody have any questions on this? I'm hoping that, so here's what I'm sort of hoping, okay? I'm hoping that before we started this unit on shear and moment diagrams, if I had started with just this problem and said construct the shear and moment diagram, it would have seemed scary. But I'm hoping now it's not. It really isn't. It's just the same thing with everything else, you know? We got concentrated loads, distributed loads, we got concentrated moments, we got overhanging beams. Like, it's really not that hard. It's the same thing as everything else, right? It's the same process, okay? Does that make sense? Any questions on this problem? Okay, let's do our next one. Okay. Okay. All right. So this problem is a cantilevered beam. We haven't constructed a shear and moment diagram for a cantilever beam yet. But I'll tell you that the construction of shear and moment diagrams for cantilever beams is probably one of the easiest problems that we do. In fact, I'll say this, cantilever beams in general are typically very easy problems. They really are in structural analysis. They are among the easiest problems that we can come up with. I mean, I'll go ahead and say it. I'm usually tempted to not put cantilever beams on exams because they're so easy. I didn't say that. You're like, well, thanks, Dr. Mike. No, I mean, in all seriousness, there's not a lot that you can do to introduce challenge in a cantilever beam problem, just because of the nature of the analysis. Now, again, I'm giving you the reactions here, but we already did this. We computed reactions for cantilever beams a long time ago. One of the things that we found with cantilever beams, because all of the reactions are all collected at a common point, you don't have to be strategic like you have to be with simply supported beams. You know, you sum moments here so that you can solve for this reaction, and then sum verticals to get the other reaction. You know how you have to be strategic? You don't have to be that way with the cantilever beam. And we were able to get all three. Now, remind me, so that I'm, refreshed here, why do we have a horizontal reaction here? Why do we have the 6 kips going to the right? Why is that there?
Because it's opposing that middle force that has some.
So you're telling me this has X and Y components?
That's nice.
Okay, that's good. Let's take a look at that. Right? That's what's going on, right? So let's take a look at this. This 6 kips and this 6 kips, I'm just curious. What is this 6 kips doing between here and here? What's it doing to the beam?
Compressing it.
It's putting it in compression, right? So if we wanted, we haven't been doing this, and I think some of the homework problems have mentioned this, and an axial force diagram. Have y'all seen this in the textbook? So if we wanted to, and I'm not going to make anybody do this, but if we wanted to draw an axial force diagram, maybe what we would do is draw it like this. Like 6 kips in compression in this region and then nothing else, right? So we haven't really been talking about that, and a lot of times we don't really even need to. Like, for example, for trusses, what would the axial force diagram look like for a truss member? It would just be, 50 kips in compression or 80 kips in tension across the whole member. It'd be pretty boring, right? So it would just be like a constant value everywhere, and which is why a lot of times when we did truss analyses, we didn't draw an axial force diagram. We just said that member has 40 kips in compression, this member has 30 kips in tension, this is a 0 force member, and that's all we needed, right? So if we wanted to draw an axial force diagram, we could draw it and probably look something like that. I just wanted to throw that out there. But the other reason I wanted to mention that is when I'm drawing the shear diagram, which do I need to be paying attention to? The 10 kips or the 8 kips? The 8 kips. The shear diagram is a reflection of the change in vertical forces. The 10 kips is not acting vertically. It's acting at an oriented angle. It's 8 kips that's acting along the y-axis. So that 10 kips sort of doesn't exist for the purposes of drawing the shear diagram. Okay. Actually, hold on, let me make that a little lower. Okay. Oh man, I can do better with that. It just did not look neat. Okay. So this is my shear diagram. Let's draw my shear diagram. Okay. So I start out at 0, okay? Tell me what to do. Up how much?
28.
Okay, so you're telling me to go up 28. Why aren't you telling me to go up 6? Or why aren't you telling me to go up 480? Why are you telling me to go up 28?
That's the force in the y direction.
That's the force in the y direction. So we're ignoring everything else. Okay. So let's put some letters on here. What happens from A to B? Nothing, right? So from A to B, we have absolutely nothing. Tell me what to do at point B.
Down 8.
Say it again.
Down 8.
Down 8. So if I'm at 28 down 8, that's going to put me at 20. From B to C, what do I do?
Nothing.
Nothing, just horizontal. And then back to sea level. Now, does anybody see a problem with what's coming next, integrating the shear diagram? What's the problem?
It's never going to go back down. It's only going to go up.
We're only going to have positive area, right? I mean, this is the first time this has happened. We haven't had a shear diagram that's been absent, that hasn't had any negative area. It's always had some positive area and some negative area, and it's always, for the most part, balanced out, at least until today. But this is way off the beaten path. It's all positive areas. So let's integrate this. So what are we getting for this region and this region? This region's 28 times 10, which is?
280.
This is 20 times 10, which is?
200.
So when we add these, we get, and where do we see the number 480?
In the moment.
The end moment. So now, when we construct our moment diagram, and I'm sort of kind of revealing what's going to happen with how I'm doing this. So I start at 0. What do I do first?
Go straight down.
I drop down 480. And the reason I'm dropping down 480 is because these areas are going to bring me back up to 0. Does that make sense? Mm-hmm. So I'm going to go down. And then from 480 go up to 80. So it's going to put me about right here at negative 200. And so, let's see if I can give myself a little bit more room. So it's going to go like that. And then like that, right? And that's our moment diagram. Like I said, I mean, they're easy. They really are kind of easy. Next time we're going to have some fun, because next time we're going to deal with an internal hinge. And so I'll go ahead and once everybody's got this, I'll show you the problem that we're going to solve on Monday. Actually, you know what? Since we've got a little bit of time, let's go ahead and do the IF stuff so we're not rushed on because the IF stuff will be very quick and I don't want us to be rushed on Monday. Everybody got this? Okay. Let's go ahead and talk a little bit about the IF stuff. Again, all these notes are on Blackboard, so I'm not, going too far down the rabbit hole. Okay, y'all remember this? Remember this? This is the indeterminacy of a external structure, and then we have the internal indeterminacy of a truss, right? And we have these two formulas, but really what the formulas were doing was they were comparing knowns and unknowns, right? So the one I kind of want to focus on for the purposes of this is this one, okay? So M plus R, okay? So R is the number of support reactions, right? We have M. Why do we have one unknown for every member in a truss? Why one unknown for every member? Because truss members only carry one force, an axial force, right? They either carry, now that force could either be tension or compression, but there's only one force in the member along the member's axis. And tension or compression is really just a sign, like positive, negative. Okay? And then why is it 2J? Why is it 2J for a truss? Why is that the number of nodes?
There's X and Y forces.
So there's no moment at a truss joint, right? So trusses are a special class of structures where we have made some assumptions and we have baked into those assumptions some behavior that results in this, right? It results in members in a truss that carry no shear and carry no moment. It results in a joint analysis that has no moment, right? So when we classify a truss, really all we need is m plus r minus 2j, right? But what about a beam or a frame? Okay. Well, I propose for a beam or a frame, this is going to be what we do. So there's a lot here, so let's just sort of take stock of what we've got here in this expression. So remember, we have unknowns minus knowns. So for the truss, the unknowns was m plus r. Here it's 3m plus r. Why is it 3m plus r? Well, for an arbitrary member in a beam and a frame, it could carry an unknown force in the x direction, it could carry an unknown force in the y direction, and it could carry an unknown moment, right? Remember, like if you have a member and you samurai sword or lightsaber, you could have an unknown x force, unknown y force, unknown moment, right? So for every member, there is at most 3 unknowns. So the unknowns in the analysis are 3m plus r. 3 responses for every member, and then the reactions. What about the knowns? Why is this number 3 instead of 2 for the joints? Because beams can carry moment, right? Frames can carry moment. That's the difference between a truss and a frame. Frames are just beams that are connected this way and this way, right? So a frame, that connection can transmit moment, right? So every joint is going to have to satisfy equilibrium according to 3 equations. Some forces in the x direction, some forces in the y direction, some moments. And then beams, unlike trusses, can have internal hinges. So we have our expression now is IF equals the unknowns, 3m plus r, and then the knowns, 3j plus e sub c. Now there's kind of an interesting thing going on here in this box, which I'm going to get to here in a second. But so far, how are we doing? Everybody good? Okay, so this is, I propose, the formula for frames. But what about the formula for beams? Well, a beam is just a frame with one member, right? So if I have one member, that one member has one member and 2 joints. Is that fair? So if you take this equation right here and you say m is 1 and j is 2, watch what happens. So 3 plus r minus 3 times 2 is what? 6 plus e sub c, right? So this is 3 plus r minus 6 minus ec, right? So that's going to be r minus 3 minus e sub c, or r minus e sub c plus 3. Isn't that the same thing as IE? So what we've done is, remember we had an external degree of indeterminacy in IE, and then we had an internal indeterminacy for beams, an internal indeterminacy for trusses, an internal indeterminacy for frames. There's a very special case where the internal indeterminacy for a beam is just the same thing as this formula. And this also works, so some of you might go, well, what if you had a beam that had multiple spans, right? Let's say you had, I don't know, a beam like this, and you wanted to consider it, you know, like that, right? Well, for however many members you have, the joints is going to be the members plus 1. And so you can keep M as M and J as M plus 1, do all the algebra, you'll still get that because the M's will cancel. So it'll still work out. Doesn't matter if you have 1 beam or 100 beams all lined up. But if you have 100 beams, you have 101 joints. So it'll all cancel out. In fact, the FE reference manual actually only lists 2 formulas. It lists IT and this one. Because you can take M equals 1 and J equals 2 and get IE. So the more you know. Sound good? All right. So what we're going to do next time is we're going to handle internal hinges. And here's the funny thing. I love this slide because the question I ask is, how does the presence of an internal hinge affect how you construct a shear and moment diagram? And the answer is, it doesn't. Okay? Here's what an internal hinge does. An internal hinge provides a specific known equation of condition, and we use that hinge to compute the support reactions. Okay? Then we just use those support reactions to construct the shear and moment diagram. And if you do everything correctly, you will find an interesting result on your moment diagram where that hinge is. And we are going to explore that on Monday with this example. Okay? So with this example, I didn't give you the reactions, so we're going to do it start to finish. We're going to compute the reactions, compute the reaction here, use the hinge, draw the whole thing. Okay? So Monday, this is going to be an example. Okay? We're going to find a really cool, but does this look intimidating? Good. It shouldn't. That's the whole point. It shouldn't look intimidating. Would it have looked intimidating 2 weeks ago? That's the point. We take it and we ratchet it up. Okay, I'm going to pull up the code one more time, everybody, but that's all I got, everybody. Y'all have a wonderful weekend. I will see you all on Monday.